at notes, and then we'll go into, homeworks, and then we'll go into notes. First thing is, we've already covered and went over together homework number 1 together. Then it looks like homework number 1 has a video. Homework number 2, we started it, and we started going over homework number 2, so we'll take a glance at that. Then homework number 3 and homework number 3 as well. So I'm going to go ahead and skip over those videos and take a look over here at our homework. We're going to skip around and go through it, and then eventually I will post, like I said before, those answers on D2L for you. That's my goal today. First thing, as a quick reminder, when we're stopping thinking about this, just kind of pulling this back of what we know already, we've got pretty much so far what we talked about, 2 different types of bonds. Bonds are either ionic bonds or covalent bonds. Covalent bonding is going to have a non-metal and non-metal, and they have prefixes that you must use for the first word and the second word. Now, because of that, you do not reduce covalent bonding. So you don't do this crisscross method, you don't reduce any of that, that's ionic bonding. And you're going to use those prefixes, except the first word, we will never use the mono as a prefix, just tossing it out there. Other than that, we are going to use a mono for the second word, if that's a situation or a case that would come up. Ionic bond is going to be a metal and a non-metal, a transition metal and a non-metal, a metal and a polyatomic and a polyatomic. What I'm trying to say is they actually have charges. They accept and they donate electrons. It's the ion or the anion that goes first, then the cation goes second. Okay? Let me double check it. I'm lying. The cation and then the anion. So the cation is always the positive one. The anion is the negative one. Forgive me on that one. But even polyatomics can have charges, okay, which so happen to be nonmetals that are bonded together. Now, as a quick reminder, I passed this up, but covalent bonds, they actually share electrons. They do not accept and donate electrons, right? So taking a glance at our homework over here, number 3, hopefully you had an answer of something like dihydrogen.
Monoxide.
That's it. Oh, whoa. Ooh, I almost wrote 2 letter O's for a second, right? So in that situation, what we're going to do is we're going to drop one of those at first vowel and leave the second one there. There are a couple of exceptions and just a couple of the way people talk or just what has been the norms. We have kept both of those vowels, A, E, I, O, and U. The next one after that, we've got the number 4. We got a covalent bond. The number 4 and number 10, we're not going to reduce those numbers at all, but what we're going to do is we're going to keep those numbers, name those. I got tetra carbon.
Okay, so you don't simplify. It says
I almost messed up on that. I almost wrote mono. Tetracarbon, tetra meaning 4. We are not going to reduce because it's a covalent bond. And then we got 10 hydrogens, and I almost screwed up on that 10 for a moment. So I said deca. Woo, I needed to come back for a moment. Deca. And what is our thing over here? Hydrogen. It starts with an H, so we should be good. Hydride. Yes.
So I'm just curious.
Uh-huh.
The prefix for 9 atoms, would it be nano? Nano. Okay, that one.
But what do we do with those vowel and vowel? If it's like, let's say it was 9 oxygens.
Oh, you just get rid of the A.
We would get rid of that A, and then we would put that O and leave the O there. But again, though, sometimes when you Google things, or it's 2025, let's be honest, we're about to hit 2026 in a few weeks, New Year. The problem is when they came out with these rules were, these rules are old, like ancient rules compared to 2025, 2026. I mean, you can't sit there and go back to 1992 and think, oh man, this, word that's used as a slang slang word now is gonna come around. You know, we didn't know back then the way people even talk now. So a lot of these rules are older rules that we have like gone away from, and because of our quote unquote norms have changed. I'm just gonna skip around. I'm gonna come over here and I'm gonna look at number 10. That's an ionic bond. Let me just keep going through this one. We got phosphorus and we've got bromide or bromine. That's gonna be a covalent bond after that. We've got a covalent bond, number 13, ionic bond, because calcium is a metal. We've got carbon, it's covalent bond. Tetra, and I see, well, that's DE. That should be not DE. Oh, well, it is a DE. That's good. We've got tetra. I see a prefix, covalent bond. I see a di, covalent bond. I see iodine is a covalent bond. Yes, it's a diatomic, but it's still considered to be a covalent bond with two iodines that are bonded together. Then the next one after that, number 19, I see a covalent bond, ionic bond, ionic bond. Iron is ionic bond, and then aluminum is a ionic bond. Even though it's on those metalloid stair step, it still is considered a metal, and it has a positive charge. Let me go ahead and just work my way up, and I'll just skip through some of them so that way I'm not consuming up all your time. Aluminum is in group number 13. I might be wrong off the top of my head, but it is a +3 charge. It is on the stair steps of metalloid. Chloride is going to be chlorine and -1 charge. We crisscross ionic bonds, and so that's going to be AlC. I agree, Cl3, absolutely. Yes, sir.
You only simplify ionic bonds.
Only simplify or reduce ionic bonds. Absolutely, yes, that is true. Iron 3, this Roman numeral 3, is a +3 charge. We know that all metals, all metalloids, well, not metalloids, but I'm screwing that up. All metals or transition metals was the word I meant to say, have a positive charge. They are cations. Oxide is oxygen. Oxygen has a -2. Crisscross those, they cannot reduce anymore. So iron, which is going to be Fe2O3. Hopefully that's what you got. The next one over here, number 21, it's also an ionic bond. I needed to find the charge, which is +2, a -1 for nitrogen. Crisscross those, they cannot reduce anymore. And it's not nitrogen, forgive me, it's ATE, so that's a polyatomic. I'm going to crisscross those over, SR1, but the 2's coming over to the polyatomic, so I must include a parentheses, NO3 parentheses, and then I can bring the 2 over. Okay, the next one after that, again an ionic bond, so I need to know the charge. That is a +2, and that is a -1 charge. Let's crisscross those down, and this is going to be BA2, forgive me, 1, BA1. This 2 is coming over for the polyatomic, so I'm going to use my parentheses, hydroxide. There we go. Selenium, we're over here finally to a covalent bond. So prefixes matter because I do not see anything in front of it as a prefix, and that means it's the number 1. So for this, it would be SE, but we do use the mono as a prefix for the second word, which is going to be oxygen, and that's a 1. You don't put a number 1, they're there invisible. All right, and then iodine, as a quick reminder, iodine is a covalent bond, or we also call it a diatomic. Don't forget there's 7 diatomics out there. We start off with hydrogen, who is way by himself in group 1. Then we go to number 7. We go over to group 7 and count down to the end of the 7, which is called the 777 rule. And so for this situation, it's going to be an I2. All right, I'm going to turn the page and go to the next page, just so that way I'll put those later on for you. It's still more naming, okay? Again, I started off when we did this homework, hey, even though it doesn't say this on the side, I think it's a good suggestion or good practice to go ahead and have it as an ionic bond going to be charges because they accept and they give up and donate electrons. Covalent bond shares electrons, but in our last unit of notes, they did mention that there's this thing called a polar covalent bond, meaning that they do share electrons, but they share unevenly, right? So that does exist, but they're still sharing electrons. So we got nitrogen and we have oxygen for that one. It's an ionic bond. Ionic's not going to share. Ionic is going to accept and donate. Also, don't forget, as a quick reminder, when it comes to ionic bonds, we are also going to, what's the word? Accept, donate. We're going to reduce. My mind went blank for a moment. So, I see that this is a polyatomic. They want me to name it. I don't need any prefixes on it, not a problem. For ionic bonds, we just name the first element as is. And then, if it's a polyatomic, you just name the polyatomic. If it's not, because it's just an element like this next one on number 5 here, where it's oxygen, you're going to use the root word and end it with an "ide." Remember that? So that was in our notes. So let's go ahead, and this one, K is potassium. So we're going to write out potassium as is. So, where is my... formula chart? So here we go, potassium, so Potassium, potassium. And this one's a polyatomic, NO3, so you've probably done that. What is it? Nitrate. And then we leave it as is. We don't change the ending of this polyatomic when it's an ionic bond. Well, we do when we get to acids and bases, right? Well, acids. Let me move that out the way. And I might be wrong, but this one still has more practice of naming, but we get to some acids. And so I think we need to get to a little bit of those acids just to kind of get a little reminder of these. So here we go. First thing, all acids begin with a hydrogen. The other thing that we already know, but you can look on the periodic chart, is that hydrogen is in group 1 and it has a +1 charge. And because this is going to be a charge or a bond that's going to be an ionic bond, because hydrogen, even though he's not a metal, he has a charge, we're going to crisscross it over. So hydrogen is always going to crisscross a +1, but those other, well, it could be an atom or an element, however you want to call that, that can crisscross over, or it can be a polyatomic. But when it's a polyatomic, it matters. If it's an 8 versus an 8. Us. There you go. So you might want to write that down or have that. Remember, I ate a poison it, or ick. I ate a poisonous bite. Ick. I ate a poisonous bite.
Crazy part is I just found out what that meant.
So, here we go. In our notes, our homework over here, just looking at this, these are all our actual names, and they wanted us to write the formula for it. Now, to be honest, you can probably go ahead and just write an H for all of them, because they're all going to be an acid, 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 and acid. Remember, if it's a binary acid, or if it's a ternary acid, you're still going to put an acid at the end, and that's going to be the second name. So we're going to have hydrogen, a hydrogen, a hydrogen, a hydrogen, 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 hydrogen. Is it going to be a binary where it's just an element, or is it going to be a polyatomic? So for an example, we've got, this one is HC2H3O2. This,
Well,
yes.
that one is confusing, because why doesn't the H at the beginning go with the H that's in the middle?
Because that's a really good question. Hold up for a moment. Do y'all see what Daniel was saying? Why aren't we combining these H's? Because this H is part of polyatomic. They have to stay together.
Wait, so would you put parentheses around that?
We would if H was going to shoot over a charge of a 2, for an example, or a 3 or something, because H is only gonna shoot over a +1 charge, we are never gonna use parentheses around that. But if I come over here and I see a hydro in front of it, right? Then it's just gonna be an element, or just, sometimes I think of it as an atom or an element, and that's gonna be bromine, over here, so Br. Then I'm gonna come over here, I don't see a hydro, no hydro, oh, hydro, no hydro, no hydro, hydro. So those ones with hydros is just going to be pretty easy. You're just gonna go ahead and give me that element that is coming over. Now, if this element, like chlorine or fluorine, had like a -2 charge or something like that, then we would have a little 2 or a 3 over here. But if it's in group 17, then it would have a -1 charge. Is one of them not in the correct, do they have a different charge?
No, I'm just curious.
Oh, okay.
Let me ask
Let's
you,
see.
Would you only do the hydro for the,
Or it'd be a halogens.
Okay.
halogens? So only for halogens, or do you have like 2 hydrogens?
Hold up one moment. So I'm gonna just double check. Br, it's in group 17. Cl, group 17. F in group 17. So they're all gonna just look like that.
So every single binary acid is part of the halogen group?
Not necessarily. They could. If it is in the halogen group, then it's a -1 charge, and it's gonna cross over, and it's gonna be a 1 and a 1.
So you can have never mind.
I was just curious how you'd write down if you had something with like a -2 charge.
Well, then you would just put a 2 on the H.
What would the name be then? Or what name of it?
Then it would be a hydro, then the element, and then acid.
Okay.
If it's in group 16, right? Then it would, then it would have a 2 over here. Acosta, what did you say? I'm so sorry. I was listening to Daniel. I know you said something earlier. Yay or nay? Nay. Okay. I thought you did. I just wanted to make sure. Over here, though, because they don't have a hydro in front of them, no hydro, no hydro, then that means that they're going to be at H plus a polyatomic. So now we need to come over here, and that's where we're going to look at this ending of the polyatomic. This one's OUS, and this one's also OUS. So we went ahead and wrote a little cheat right here. If it's OUS, then it's ITE whenever we have to look it up over here on the polyatomic chart. So I'm going back to my polyatomic chart to go and see who it is, because that's going to help me OUS. I need to look for an ITE, for an example like that, ITE or ITE, for an example. So over here I've got BR, then this one over here is H, oh wait a minute, 2SO3. And remember that SO3, which is the polyatomic, is not going to have parentheses. Why? Because the hydrogen had a +1 charge that crisscross over. Yes, ma'am. Oh, well, let me double check. I could have messed that one up. SO3. So let's take a glance. And it needs to end in a, if it's an us, then it ends end in an 8. ITE. Right here. SO3 is a -2 charge. I crisscrossed it over. This one, hydrogen has a +1 charge. SO3 has a -2 charge. I crisscrossed those over, and that's where I got the 2 from. Mhm.
This one is, if it has a +2 in the ionic bond. +1 and -2, that would mean it's an ionic bond, right?
It
work
is.
with what?
It is. I guess you can call it. It's an ionic bond, as in the fact that it has charges. The fact that this one has hydrogen with it, it is an
You
acid.
can just treat it like an ionic bond.
Yes. We would end up treating it like an ionic bond. It's a special ionic, which is an acid. So yeah. Next one over here, I see that, remember how we just said there's no hydro, it ends in an OUS, so that means that I need to look for an ITE, and then I need to also kind of look to see, hey, does it have a charge, or what charge is it? It's going to have a charge. I know hydrogen is a +1, so I need to come over here. This is going to be ClO, and it actually is ClO2. Let me see, ClO2. And it's an OUS, so it needs to end in an ITE. ITE, it's a -1 charge, so -1 charge, crisscross that over, so no number behind the H, then it's just going to be ClO2. Okay. The next one, well, we already did, but let's skip down. This one again, polyatomic, polyatomic. How do I know they're polyatomics? There's no hydro in the beginning. But I do know that even though it's an acid, it's going to have a hydrogen to start off with. So then, in that situation, I'm going to come over here, look to see what the ending is. I see an IC and an OUS. Okay, IC means that it originally was an 8, and OUS means originally it was an ite. So I need to come over here and I need to see which one is that going to be. This is going to be PO4, and this one is NO2. Okay, they're actually a +1, -1, +1, -1, crisscross those over as well.
Is phosphoric
Oh.
acid, what is
Phosphate has a-
H3?
It has a 3.
Yeah.
Good call. There you go. Then let me double check. NO2. I have NO2 right here. -1 charge, so -1 charge. Alrighty, so just kind of a quick review and just looking at our homework for a moment. Homework number 3, that should be the end, and then homework number 4 goes into moles. Now, I'm going to move the homework out of the way. I'm going to leave my polyatomic as well as my formula chart. Specifically, I'm going to roll it over to this one with our mole chart, and that's where we ended up at last time. So, moving my homeworks out of the way, I will post those answers later on today. That is my goal before I leave. I want to take a glance at my notes. Alrighty. There. So in our notes, okay, so here's where we're at and here's where we left off at. We actually left off with our mole chart. That's what we call this, a mole chart. And just as a quick reminder, we already talked about moles, but if you start off with the mass with grams, that means that you're going to go take a glance at the periodic table. If it's a compound, you're going to add all of those atoms' masses together. If it's just an element, then you're going to go look, like if it's aluminum, go look at the mass on the periodic table. Now this is equal to 1 mole of anything, whether it's an atom, whether it's a compound, or whatever. Now, we can break this apart, but after that, 1 mole equals Avogadro's number. Just like 1 pair of shoes equals 2 shoes. Just like 1 dozen of eggs equals 12 eggs. Just like a baker's dozen equals the number 13. Okay? So, that's what this is. 1 mole, or think of it as 1 pair of shoes, equals, for an example, 2 shoes individually. Now, over here, though, we can break this apart into a little bit more specific. It either is atoms and diatomics, or it's either going to be what we call compounds. There's 2 types of compounds. In general, our compounds are going to be covalent compounds or ionic compounds. I do want to mention that Daniel had a really good suggestion, or he had said something. He's like, so that acid that was bonding, it's like an ionic bond. It absolutely is. It has a positive charge and a negative charge. All bonds are pretty much going to be either in the covalent group or the ionic group. Either they're sharing electrons or they're giving up and accepting electrons, one or the other. And so we said because we already know, when we already use these words, MC and FUN. MCs are called molecules, which are covalent bonded compounds, and FUNs are going to be what we call formula units, and those are ionic bonds where they accept and donate electrons. Now, to break it down even further, that compound, for an example, let's think of a molecule, which would be H2O, for an example, okay? If we want to be a little bit more specific, and let's say I have a gallon jug of water that I bought from HEB. So I have this gallon jug of water, and I can go and put the gallon jug on a scale, and I can see how much the mass of it is. And I can break it down, and I can say, this mass of the gallon jug of water equals 1 mole, or however many moles are inside that gallon. Those moles equal Avogadro's number, and if I tell you how many hydrogen atoms or how many oxygen atoms are in it, I can ask you a very specific, and that's what we're getting to now. But let's say sodium chloride, which is table salt, okay? If I tell you, hey, here's a whole container of table salt, right? We can put it on the scale, we can figure out how many moles I have. From that, I can figure out using Avogadro's number, how many FUN molecules of NaCl, sodium chloride, I have. And then I can be very specific. In this whole container of table salt that I just bought at HEB also, how many sodium ions are inside the whole container? Very specific. Now, we're getting specific because we're going to get to what we call in chemistry stoichiometry. That's like our ultimate goal in chemistry, is what we call stoichiometry. Stoichiometry is a way to actually kind of do a little inventory. Okay, so second semester is stoichiometry. It's trying to say, hey, I need you, for an example, to go to the grocery store, and we're going to have this big old party, for an example, and we're going to make ham and cheese sandwiches. I don't want you to spend extra money. I want you to make exactly 50 sandwiches. Well, you know, for an example, you can break it down. Okay, if I'm going to make 50 sandwiches, then how many slices of bread am I going to need? 100 slices of bread. Does that make sense? Okay, so that's why we're getting down to very specific, because imagine if the compound is the sandwich, and the sandwich has bread, slices of cheese, and slices of meat in the sandwich. That's what makes the sandwich. It's a compound. Think of it that way. Well, why? Companies don't want to end up like, well, I guess I'm going to need this much of this chemical to make what I need to make. They don't want to buy extra, or they don't want to buy extra and spend the money, and then they have all of this extra chemical, and it can go to waste. Does that make sense? Or what if they don't buy enough? What if you only bought 2 loaves of bread, and you're like, that looks like 100 slices, but it wasn't 100 slices. It was only 80 slices. You should have bought 3 loaves of bread. Now you've got to get up, take time away from getting the party set up, because you got to go back to the grocery store to go buy another loaf of bread. So quit wasting that time. Get what you need to get the first time, so that way you're not wasting time and wasting money. And that's what it comes down to companies. Whether you're a pharmaceutical, legit pharmaceutical, or whether you're a street pharmacy person. You don't want to waste that time having to go back out to the stores or wherever you need to go so you can buy the rest of your chemicals to make whatever compound you need. Hopefully that makes sense, right? You're going to be efficient with your time and money. So that's what we're getting down to. Atoms and ions, okay? Again, don't forget, atoms share electrons, ions accept and donate. And when we're looking down to the atom or ion level, we're going to use that little subscript, which is that little number at the bottom. So we're going to look at the little number is what I wrote, or we use the subscript. So here's where I'm at this moment. So let's go ahead and start filling in these notes now. It says here, let's go ahead and let's do a little bit of conversions or a little bit of math. We want to start off with, and we want to say, how many atoms of oxygen? Okay, so we're looking for question mark, oxygen atoms, or O2 atoms, that are in this much, 67.8 grams of H2O. So using the mole chart over here, where am I starting and where am I going to? I am starting off with grams, which is all the way to the left, and I'm going to take, remember, we can't just skip a step. We have to go step by step by step when we do our math. We need to go from mass to moles to Avogadro's numbers, and then we're going to go to atoms, which is over here, because H2O is a covalent compound. Okay, so we're going to take every single step by step. Right now, write down what you start off with, just like we've done before. We're going to do our little line, and we're going to go ahead and do our little breaks in between it. So 67.8 grams of H2O. Well, just like algebra class, if I have grams of H2O and I want to cancel that out, well, I have to have grams of H2O at the bottom. So I'm going to go ahead and write over here grams of H2O. Now, using my mole chart again, where does it say I'm going to find this number magically? It doesn't just pop to the sky. You actually have to do a little work. And it says up there, you're going to use the periodic table. So I have my periodic table over here. And so here's my periodic table. Where am I looking at with my periodic table? I'm going to look. I agree. We're going to look at that number. We're going to look at this number right here and this number right here. So I'm going to come over here and I'm going to say, well, hydrogen and oxygen. And that's really what my compound is made up of. And I'm going to say, well, I've got 2 hydrogens and 1 oxygen. Looking at the mass number exactly like she said, I'm going to come over here and say, this is 1.01. And we like to, you do not have to, round to 16. Or you can put 15.999. Go ahead and do the math. This comes out to 2.02. This comes out to 16 times 1 is 16. Add them together. I want the molar mass of all of the whole compound together. And that comes out to 18. Yep. I agree. So there goes our mass of what 1 molecule of H2O is. 18.02. So I'm going to come over here and I'm going to write this magic number of 18.02 equals, using my mole chart, this equals 1 mole of H2O. So the good thing here is now my grams cancel out. I'm left at moles, but unfortunately I don't want to stop at moles. I want to go to atoms, specifically the oxygen atoms. Now I'm going to go ahead and do another line so I can break this apart. And if I've got moles at the top, then I need moles at the bottom. So 1 mole of H2O equals, it says right here. Well, I'm not going to go over there. I agree, Avogadro's number. We're going to come down because it's a compound. So Avogadro's number, which is 6.02 times 10 to the 23rd MCs of H2O. My moles get to cancel out. I'm left with MCs. I don't want MCs. I want atoms of oxygen specifically. Okay? Not a problem. So what I'm going to do now is I'm going to come over here, do another line. Remember, if I have MCs of H2O, well then down here I need to have MCs of H2O. So that way, algebraically, they can cancel each other out. But this is going to be the new step for us, because Avogadro's MCs equals, well, now I need to come over here. 1 MC equals, well, how many atoms of O2 do we have? And why did I put a little 2 behind the O? Because O is a diatomic. So how many atoms? Wait a minute. Let's take a glance. I'm going to, just for my sake, I'm going to come over here, and I knew I had a yellow highlighter this. I'm just going to go ahead and I'm going to highlight the compound I'm talking about. H2O. How many O's are in that compound? I agree. Use the little, look at the little number, use the subscript, which is, say, Daniel?
1.
Which is a 1. 1? There's only one atom of oxygen in an H2O compound. Now, my MCs get to cancel out, thank goodness. I'm left with atoms of O2, which is what I wanted. I get to stop my math. Go ahead, multiply everything at the top, multiply everything at the bottom. Imagine this as a big division sign. Then you can divide those numbers, my suggestion, or you can shoot it all in your calculator at one time. I'm going to go ahead and move this over to the side. I'm going to write the answer. The best way, you do not have to pull out a calculator, right? You do you, but I suggest you should practice typing it into the calculator and see if you get the same number as us.
And the thing would be atoms of O2.
That is it. The SI unit, or what you're going to write behind the number, is atoms of O2. 100% correct. I'll give us like another 20 seconds or so. I'm watching the little red hand. But you should practice.
It's getting cold in this corner over here. I'm so good. I got it.
You do? Okay. Ready, set, take a glance.
Yeah, that's what I got.
Whoop, whoop.
Exactly.
There you go then.
There we go.
So it was what we were doing before, but now they are trying to differentiate exactly, we're getting down to the actual atoms or ions that are in that compound. Again, like I said, if we're going to make, for an example, 50 sandwiches, and each sandwich is going to contain one slice of cheese, when you go to the grocery store, if the packages are sold in packs of 10, how many packs do you need to buy to make 50 sandwiches? And it's sold in packs of 10. You should buy 5 because you're going to end up with exactly 50 slices. Don't buy 6 because now you're going to have leftover, and cheese does expire. You know, you don't want it to expire.
I hate cheese.
Especially if you hate cheese like that. You know what I mean? So that's the reason why we're getting here. We're getting here not only for the legal pharmaceuticals, but for those street pharmaceuticals that do not know how to purchase the proper quantities of what they need. You know? So let's turn this page. Thou shalt not be a street pharmacist. Remember that. I don't remember. I made it yesterday. I printed it yesterday. How much time do we have?
We have approximately
30 minutes.
not 30
Less than
minutes.
30 minutes.
27? Oh, okay. I appreciate that. Okay. 20-ish minutes. Let's go ahead and what we'll do, we'll go over the quiz on Friday, and then we will go ahead and do a little bit more notes on Friday, and then next week we'll knock out the rest of the notes. Perfect. That was a perfect question. I think that was the perfect.